Hello! Today I'm going to do a Newton's second law free body diagram type of problem, so let's get started. We have a 65 kilogram person in an elevator standing on a scale. The elevator and the person and the scale, the whole system, is moving downwards, but it is decelerating at 3.0 meters per second squared. We want to figure out the scale reading. Okay, there are a few steps I always like to use when I do this kind of problem. The first one is to draw a free body diagram on the system. So let us do that right away. So the forces that are acting on the person are going to be gravity pulling them down and normal force pushing them up. And then after I've drawn a free body diagram, I like to choose a coordinate system. That is step 2. The coordinate system I will choose is to have upwards be positive y and downwards be negative y. It's kind of up to you which way you have be the positive or negative direction. I like to have upwards be positive just because that's what I'm used to, but there are some problems where it's easier to have positive be downwards. If this were a two-dimensional problem, I would also have to choose a direction for x, but since there are no forces in the x direction, I'm not even going to worry about that right now. All right, so first step was free body diagram. Second step was choosing a coordinate system. Normally I would have a third step in here, which would be to find components of forces, but we don't have to do that this time. And the last step for this one is just to sum up all the forces and set them equal to mass times acceleration. All right, I have to be a little bit careful here when I plug in my acceleration. The elevator is moving downwards, but it is decelerating at 3.0 meters per second squared, which means that the direction of acceleration is actually upwards. So my acceleration is positive. It's always important to bear in mind that positive acceleration doesn't mean speeding up. That's not what it means. It could mean that if the thing was moving in the positive direction. All it means is that the net force is in the positive direction. Really, what I should have drawn is for the normal force to be bigger than gravity. I don't always worry about these being to scale, but it's not a bad idea to do that. So my acceleration is going to be positive here. The mass of the person I am given is 65. I'm going to look at the other forces in play. So I have normal force and gravity, but I might not even plug this in as normal force because what's important here is to think about what is actually causing the normal force. What's putting the normal force on the person is the scale. The person is pushing down on the scale and the scale is pushing back. By Newton's third law, those have to be equal forces. So I know the reading on the scale is going to be equal to normal force. So I think I'm just going to plug this in as force on the scale. That's my upwards or positive force. Gravity is going to be my negative or downward force. Now I need to plug in what f of g is. Fg is always m times g. G being a constant telling us the strength of gravity. It's also the acceleration due to gravity. And I will continue this over here. I'll plug in the numbers for mg. And I'm going to move mg over to the other side. I'm subtracting mg from both sides. Or actually adding, sorry. Okay. So m times g would be 65 times 9.8. I'll go plus 65 times 3. And I end up getting that the force from the scale is 832 newtons. That's a pretty big force, but this is actually a pretty big acceleration. Well, most elevators wouldn't have you accelerating that fast. And that is all we have to do. All right, feel free to leave questions in the comments, and I hope this was helpful.